Chocolate isn't made in a factory. It's engineered, from bean to perfection. Before it melts in your mouth, it survives heat, pressure, and science. This is not candy. This is chemistry, machinery, and precision.
Every piece of chocolate begins far away from factories and machines, deep in tropical regions near the equator. The cocoa tree, scientifically known as Theobroma cacao, is delicate and demanding. It requires warmth. Inside each cocoa pod are the seeds that will become chocolate. But at this stage, they contain no chocolate flavor at all.
Cocoa pods must be harvested by hand. Machines cannot distinguish ripe pods from unripe ones.
Harvest timing directly affects flavor. Unripe pods lack sugar. Overripe pods risk spoilage.
The beans are removed quickly after harvesting. That white pulp isn't waste, it's fuel. It's natural.
At scale, thousands of tons of cocoa beans begin their journey this way every day. Before machines refine.
This is where chocolate truly begins to form, not in steel machines, but in controlled biological transformation.
Chocolate flavor is not created by roasting alone. It begins here, during fermentation. Without this step, natural sugars in the pulp feed yeast and bacteria. As microorganisms consume these sugars, heat is released, raising temperatures up to 50 degrees.
Beans are regularly turned to introduce oxygen. This shifts fermentation from yeast-driven reactions to bacteria.
Inside the bean, acids break down proteins and carbohydrates. These reactions create amino acids and sugars.
Once fermentation is complete, moisture becomes the enemy. Beans must be dried carefully to stop
microbes. Sun drying relies on weather and time. Industrial dryers use controlled airflow and temperature. Both aim for the same
version of sant and word at which word and layer to the evil kilometers follow loisin state of the beaver crying could trouble thousands of chocolaters.
At this point, flavor has been created top thwart, but not revealed. Next, heat and
Once cocoa beans reach the factory, the goal shifts freshing.
Before heat is applied, beans must be cleaned. Stones, dust, and plant debris can damage machines and contaminants. Magnets capture metal fragments. Optical sensors detect abnormal color and size. These systems ensure only roasting is where chemistry takes over. Inside these rotating drums, temperatures rise between 120 and 150.
Heat activates the Maillard reaction, a chemical process between amino acids and sugars created during.
Once the desired roast is reached, heat must be stopped instantly. Forced air cooling prevents over-roasting and locks it.
Now fully roasted, the beans carry aroma, but they are still structurally whole. Next, machines will break them apart.
Roasted cocoa beans still contain their outer shell, a fibrous layer that adds bitterness and contamination if left behind.
Cracking machines apply controlled mechanical force. The goal is not to grind, but to fracture. After cracking, particle size becomes critical. Pieces that are too large won't separate properly. Pieces that are too small risk losing cocoa solids.
Winnowing uses physics instead of blades. Airflow lifts lighter shell fragments upward, while heavier cocoa nibs fall down.
Shells are immediately removed through vacuum systems. Even small shell fragments can ruin texture and introduce unwanted bitterness.
These cocoa nibs are the heart of chocolate. They contain cocoa solids and cocoa butter, the two components that determine flavor, texture, and melt. Quality control teams monitor shell content down to fractions of a percent. This level of precision ensures consistency across thousands of kilograms of chocolate.
At this stage, cocoa is still solid, but friction will soon change everything. Next,
cocoa nibs look dry and solid, but nearly half their weight is fat. The purpose of grinding is not just size reduction.
cocoa butter melts at just above human body temperature. As friction raises internal heat, fat
ball mills take over for fine grinding.
Steel spheres collide with cocoa particles thousands of times per minute.
Texture depends on particle size. If particles are too large, chocolate feels gritty. Industry standard.
At this stage, cocoa becomes cocoa liquor, a smooth, thick liquid containing both cocoa solids and cocoa butter. Temperature must be maintained to keep the cocoa mass fluid. If it cools too much, fat solidifies. If overheated, flavor. Cocoa liquor is powerful, but too intense on its own. Next, it will be carefully blended with sugar, milk.
Cocoa liquor alone is intense, bitter, and unbalanced. Chocolate becomes chocolate.
At this stage, chocolate is an emulsion, solid particles suspended in fat. Cocoa butter coats each part.
Dark chocolate contains little or no milk. Milk chocolate balances bitterness with dairy fats. White chocolate contains mints.
As mixing continues, particles become fully wetted by cocoa butter. This reduces friction between particles.
Viscosity determines how chocolate flows through pipes, molds, and enrobing machines. Too thick and...
Formulation creates balance, but texture and flavor are not finished yet. Next, refining and conching will...
Exactly. Even after formulation, chocolate is not yet smooth. Sugar crystals and cocoa particles are still large enough to be detected by the
Refiners use multiple rollers rotating at different speeds. As chocolate passes between them, particles are crushed small.
The human tongue can detect particles larger than about 20 microns. Refining reduces particles below this threshold.
After refining, chocolate temporarily looks dry and powdery. This is intentional. Structure.
Conching is where chocolate develops its final personality. Large mixing arms knead the chocolate for...
During conching, airflow removes unwanted acids created during fermentation. At the same time, continuous movement smooths flavor edges, reducing harshness and rounding aroma. Heat accelerates flavor development piling, but too much destroys delicate aromas. Engineers carefully control temperature.
At the end of conching, chocolate is smooth, aromatic, and balanced. But it is still unstable. Next, precise temperature.
Perfect chocolate is not just about flavor. It must shine, snap cleanly, melt evenly, and resist bloom. None of that happens by accident.
Cocoa butter can form 6 different crystal types. Only one, known as beta.
Tempering machines guide chocolate through precise heating and cooling zones. This controlled thermal journey destroys uncer. First, chocolate is gently heated to melt all existing crystals. This resets the system, erasing crystal memory sources. As temperature drops, stable crystals begin to form. Some machines add finely tempered chocolate as seed material.
Once properly tempered, chocolate must remain within a narrow temperature window. Even a few degrees of error can collapse crystal structure.
A sharp snap confirms correct crystal alignment. Shine indicates uniform structure. These physical cues reveal molecular success. Tempered chocolate is stable, but still liquid. Next, it will be shaped, cooled, and solidified into the forms we recognize as chocolate bars.
Once chocolate is properly tempered, it is ready to be shaped. At this stage, structure already exists at the mold. Depositing systems control weight and volume with extreme accuracy. Each mold receives the same amount of chocolate to ensure uniform thickness, snap, and packaging compatibility.
Vibration removes trapped air bubbles. Without this step, chocolate would contain weak points, affecting texture, appearance, and structural integrity.
Cooling is not about speed, it's about control. Chocolate must cool gradually to preserve the crystal structure created during tempering. As temperature drops, cocoa butter crystals lock into place. Correct cooling ensures shine, snap, and resistance to fat bloom.
When cooling is complete, chocolate naturally contracts. This allows it to release cleanly from molds, a sign that tempering and cooling were executed correctly. Intervals. High-speed cameras inspect every bar for cracks, bloom, weight deviation, and surface defects.
Despite automation, human checks remain essential. Texture, snap, and internal structure confirm what sensors cannot fully measure.
Chocolate is now complete, but not yet protected. Next, packaging will preserve flavor, freshness, and identity. Chocolate may be perfectly made, but without proper packaging, it will fail. Light, oxygen, moisture, and heat. The first layer creates a barrier. Foil blocks light and oxygen. Flow wrap seals freshness.
These materials are engineered.
Heat sealing fuses packaging layers into an airtight enclosure. Temperature and pressure are carefully controlled.
Individual bars are grouped into cartons for protection and efficiency. Robotics ensure uniform packing speed while minimizing human contact. Palletizing prepares chocolate for transport. Load stability prevents vibration damage, while shrink wrap protects against dust and moisture during shipping.
Chocolate is stored under controlled temperature and humidity.